All right, what is up, guys? Welcome to The Explainer. If you're in 11th grade right now, listen up, because today we're diving headfirst into Mathematics Chapter 2, Relations and Functions. Now, think of me as your older brother, who's kind of already walked to this exact path. I'm here to tell you this isn't just, another random math chapter you have to memorize. These concepts are literally the essential building blocks for unlocking advanced algebra and eventually absolutely crushing calculus. So let's just jump right into it. Here's our roadmap for today's explainer. We're going to start with the Cartesian product, move on to defining mathematical relations, then introduction to functions, standard real functions, and we'll wrap it all up with the algebra of real functions. Starting off with Section 1, the Cartesian product, building the foundation. So consider this like level 1 of our math skill tree, right? Before we can build any complex mathematical models, we absolutely have to understand the foundational concept of linking two completely different sets of items together. The Cartesian product of sets P and Q is simply the set of all ordered pairs from those sets. Now, I really want you to lock onto that phrase, ordered pairs. Sequence absolutely matters here. It's kind of like a combination lock or a precise coordinate on a map. If you have an ordered pair A, B, it is strictly equal to C, D, only if A equals C and B equals D. You can't just mix and match them whenever you feel like it. The order is the rule. Let's actually make this real with a few examples. What's incredibly cool here is how easily you can predict the outcome. Just take a look at that first row. Set A has two elements, 1 and 2. Set B has two elements, 3 and 4. So how many pairs will we get? Well, you literally just multiply the number of elements. 2 times 2 equals 4 ordered pairs. And you can see them listed right there. 1, 3, 1, 4, 2, 3, and 2, 4. Now skip down to the third row. 3 elements in A, 2 in B, boom. 3 times 2 is 6 elements in that resulting set. Oh, and definitely catch that last row. If one of your sets is completely empty, well, 0 times anything is 0, so your Cartesian product is just an empty set. Pretty easy, right? All right, moving on to Section 2, defining mathematical relations, linking elements. Okay, so we've cleared level 1. This is where things start getting really interesting. We're going to take those basic Cartesian combinations we just mastered and actually start applying specific filters and logical rules to them. Let's nail down the core vocabulary first, just so these terms don't totally blur together in your head during your next exam. When you have a relation, which is basically just a subset of our Cartesian product, you've got 3 main players. First is the domain. This is simply the set of all the first elements in your ordered pairs. It's your input. Second, the range. This is the set of all the second elements, your actual outputs. And third, the codomain. This is the entire second set available to you. Just remember this. The range is always a subset of the codomain. Think of it like this. The codomain is the full menu at a restaurant, but the range is just what you actually ordered to eat. And this image here brilliantly illustrates exactly what I'm talking about. Look at this arrow diagram. It visually maps the inputs from our domain on the left straight over to the outputs in our range on the right. You can literally trace the path of the relation. Each arrow is showing how a specific rule links an element from the first oval over to the second. If an item on the right gets an arrow pointing to it, it's officially part of the range. But that entire right oval, whether arrows hit it or not, that's the codomain. Now, you might be wondering, how many total relations can we possibly make between two sets? Well, we calculate that using cardinality. If set A has P elements and set B has Q elements, the total number of possible relations is a massive 2 to the power of P times Q. I mean, it scales up incredibly fast. And what if we ever need to hit reverse? We use an inverse relation. You literally just flip the ordered pairs backwards. So an inverse relation from B to A simply swaps the elements. An AB pair just becomes BA. Next up is Section 3, Introduction to Functions, Unique Mappings. Great job sticking with me so far, guys. Welcome to Level 3, the big leagues. This is where we introduce the ultimate rule, where mathematical relations go from being just a bunch of loose links to becoming strictly predictable mappings. I want you to really think about this question. When is a relation a function? Seriously, wake up, shake off that math fatigue for a second, because this is the single most important concept in the entire chapter. Every function is a relation, but not every relation gets to be a function. So what's the secret password? Well, here is that secret password. A relation only upgrades to a function if it perfectly follows 2 strict rules. First up, the unique image rule. Every single element in your domain must point to exactly one image in the codomain. Basically, no 2 timing allowed. One input gives exactly one output. Second is completeness. Every element in your first set, set A, must be used. you can't leave any inputs behind. We write this out with a notation f of a equals b. And if you're looking at a graph, we use the vertical line test. Just drag an imaginary vertical line across the graph. If it touches the curve more than once at any point, boom, it fails, not a function.
Which brings us to Section 4, Standard Real Functions, Visualizing Rules.
Enter the boss level. We know the strict rules now, but what do they actually look like geometrically? Over on the left, we have the identity function. Whatever x is, y is exactly the same, giving us that perfect straight 45-degree diagonal line. In the middle is the modulus function. It turns everything positive, which creates that sharp V shape. And on the right, the signum function, which steps abruptly between -1, 0, and +1. Now visually run that vertical line test we just talked about across all three of these graphs in your head. Notice how a straight vertical line will never ever cross the drawn lines more than once? That visual proof right there confirms they are all perfect functions.
Finally, Section 5, Algebra of Real Functions, Combining Rules.
All right, guys, we are in the home stretch. What happens when we start smashing these perfectly behaved functions together using algebra? It's actually beautifully straightforward. You can treat them almost like standard numbers. You can add them together with f plus g, subtract them with f minus g, multiply them with f dot g, and divide them with f over g. The only hard rule here? For division, your denominator, g of x, absolutely cannot equal 0. You already know from earlier grades that you can't divide by 0. And yeah, that rule strictly applies to functions too. Once you get the hang of these 4 operations, you can combine any standard real functions together to model just about anything. And that brings us to the finish line for Chapter 2. I want you to read this quote with me. Mastering relations and functions is the first step toward calculus and advanced algebra. Seriously, let that sink in for a second. The work you put into understanding Cartesian products, mapping out domains, and visualizing that vertical line test today, that is exactly what sets you up for total victory in calculus tomorrow. You've built the foundation. The real question is, now that you know how functions combine and operate, what incredibly complex mathematical systems are you going to map out next? Keep that curiosity alive. Thanks for learning with me, and I'll catch you on the next explainer.